Okay, good morning. So I was asked to talk about beyond the standard model and looking ahead, and I thought this was a good way to look ahead. We just heard from Frank that we have not had any amazing discovery in beyond the standard model, so I will try to put in context where we are. So the idea is that we want to discover some new particles or new interactions and new ideas, more generically. And the big question is why and where, and especially where means at the Weak scale seems to be kind of disfavor. Maybe within the LHC reach, at least the starting now, phase 2 of LHC. But maybe the new physics is that the neutrino, right-handed neutrino scale, at the GUT scale, at the Planck scale. So the point is that, as Christophe was saying, new physics beyond the standard model is needed to explain many observed phenomena, dark matter, the matter-antimatter asymmetry, and actually the dynamical origin of the fermion masses mixing. And we know that in order to explain matter-antimatter asymmetry, we at least need some additional CP violation. None of the above really demands new physics at the electroweak scale or at the LHC scale. Before the Higgs discovery, we knew that we need something at the electroweak scale in order to make the standard model calculable. But after the Higgs, so the Higgs came to the rescue and is a blessing and a curse in some way. So we expect new physics beyond the Higgs boson, that's for sure. At which scale? Well, all what we know in some ways is that the Higgs is spatial, it's scalar. We know scalar masses are not protected by gauge symmetries, which means that we can always write this nice term in our Lagrangian, and this mass parameter actually becomes sensitive to any physics at the UB. And what this means is that when I do radiative corrections to this parameter, it knows about the particles that are at any higher scales up to the Planck scale. So although the standard model with the Higgs is a consistent theory, light scalars, like the Higgs, cannot survive in the presence of heavy states. And that's what is usually known as the fine-tuning and naturalness problem. And in fact, this is what theorists have been pushing quite a bit. So there are two possible solutions that we have been thinking about and building models and being very busy, especially theorists trying to earn our salary. And so one of these is supersymmetry, a fermion-boson symmetry, and in that case, the Higgs remains elementary, but it's precisely this fermion-boson symmetry that protects the mass of the Higgs from being sensitive to the UV physics. The other option is composite Higgs models, and in this case, the Higgs does not really exist above a certain scale, and at this scale, there are some new strong dynamics that takes place. And of course, there are a lot of model building in that direction as well. The interesting thing here is that both options imply changes in the Higgs phenomenology. We heard a lot from Christophe and from also the experimental speakers, how much we are trying to squeeze in information from Higgs phenomenology and Higgs properties at LHC. Of course, there are also new particles that may be seen at LHC, or we can actually have to recur to indirect signatures in rare decay processes if the mass is really beyond the LHC. So SUSY has many outstanding qualities. It allows, as I mentioned before, to solve the hierarchy problem between the electroweak scale and the Planck scale. And I will go back to that in a sec. It generates the electroweak symmetry breaking scale dynamically, unlike in the standard model that we really put it by hand by putting negative the mass square, the parameter of the mass square, allows gauge Kaplan unification, provides a good dark matter candidate that is the lightest supersymmetric particle, in fact allows the possibility of electroweak baryogenesis, generating the matter-antimatter asymmetry in relation with the electroweak scale. That is what we are probing, so that's an exciting option. And of course, it's also string friendly. So I would say that SUSY is elegant and is gorgeous. And you may decide on which side you are. But I would say that may lead us on a very dangerous journey. And more than that, supersymmetry may hide forever. So hoping that this is not the situation, we go and look at what we really have to do with supersymmetry and naturalness. So the Higgs mass parameter, as I said, in supersymmetry is protected by the fermion boson symmetry, so no radiative corrections. But in practice, supersymmetry, we know, is broken, and this Higgs mass parameter receives radiative corrections that are of the order of the mass of the new supersymmetric particles. So there are two options. If M SUSY is of order of the weak scale, is what we would like to call natural SUSY, and we very comfortably solve the hierarchy problem. Or maybe maybe it's a bit beyond, like in the TeV or so, and we can decide how comfortable and uncomfortable are we with this natural situation. But in any case, for sure, it's true that if M SUSY is much lower than MGAT, then supersymmetry solves the big hierarchy problem, even if it doesn't solve the little hierarchy problem. So being a bit more careful about what we say, the point is that not all SUSY particles play an equal role in solving the Higgs naturalness issues. And in fact, as it's shown in this slide here, Higgsino, stops, and the related left-handed bottoms, and gluinos are the special guys. And in fact, solving the electroweak symmetry breaking conditions for the Higgs potential, at 3 level we get this situation. This is actually what was before called the Higgs mass parameter. This is the Higgsino mass parameter that governs the Higgsino mass, and this is the Z mass. And so at 3 level already, we have a bound, or we need, if we want like about a 20% or so tuning, that the Higgsino is below 400 GeV. When we go at the loop level, then the Higgs mass parameter MHU, related to the up Higgs, receive radiative corrections from the stop sector, and this translates in the stops being below about 700 GeV, and then the stops actually receive radiative corrections themselves from the gluino, and so at 2 loop, this mass parameter receives 2 loop corrections from the gluino mass, and this puts a bound on the gluino below 1.5 TeV. So if SUSY is naturalness, we are starting to get a bit worried. This is Weltschmerz. It's a very nice word. That is the feeling experienced by someone who understands that physical reality can never satisfy the demands of the mind. So why didn't we discover SUSY at LEP, at the Tevatron, or at the LHC? And indeed, as we saw from Frank's talk, both CMS and Atlas are aggressively pursuing the direct signatures of naturalness in the stop sector, SBOTOM, gluino, and also in the Higgsino sector. Another way to look at the results of LHC is by looking at the global fits. There were very nice talks in the parallel sessions, and this one is one slide that shows that by looking at the most constrained models, maybe we are overlooking quite a bit. This is instead an analysis with a PMSSM, which is like a 10 parameter in this particular case. So we kind of liberate, for example, the first generation, the first and second generation as fermions from the third generation as fermions, and then we see that the things go much better, and it makes clear that the G-2 anomaly is still nearly decoupled from LHC SUSY constraints, and we hope that with a new Fermilab G-2 experiment, maybe LHC and G-2 start getting together again, and we get more information there. Another way, of course, is to look at the simplified models, and one thing I thought it was interesting about the simplified models, so this is the bound on the simplified models in the neutralino stop sector, and this is the one doing the PMSSM, so this would be totally excluded by the PMSSM, but this also, the PMSSM has a lot of connection between the parameters. So in reality, these simplified models, which do not assume any correlations, can teach us a bit. And so we need to make qualified statements about what is rule in or rule out in SUSY more carefully. So besides looking to the new SUSY particles, possible SUSY particles, of course, the LHC is also looking to new Higgs states that appear in supersymmetry and in many other extensions. In particular, in supersymmetry, that we know that the minimal number of Higgs doublets is 2, and so there is always one that is the standard model-like doublet, where this is the down and the up Higgs doublets, and this is tangent beta defined as the ratio of the two vacuum expectation values. And so this is the standard model Higgs. And then the orthogonal combination of non-standard model Higgses is given here. Strictly speaking, the CP even modes mix and no one behaves like the standard model, and these are the ones that we always talk about, the little Higgs and the heavy Higgs with a mixing angle alpha. But what I would like to stress here, that if you look at the situation when sine alpha goes to minus cosine beta, okay, you realize that the light Higgs is actually the standard model Higgs that requires a vacuum expectation value V, okay? So this is a very interesting situation, because it means that if we are in this situation or close to this situation, then one recovers the standard model as an effective theory, and it will be very hard from precision measurements of the Higgs couplings and properties to know if there is another Higgs unless we see it directly. This occurs in two very well-known situations. One is the decoupling limit, which means that all the other Higgses are heavyish, above 500 GeV, above 600 GeV or so, and then the light Higgs is very standard model-like. However, it's another situation which I would like to draw your attention to that is called the alignment limit. This occurs for certain values of the Higgs quartic couplings and tangent beta, and this means that we acquire this relation where this Higgs becomes the standard model Higgs, but the other Higgses are independent of how light the other Higgses are, okay? And this is interesting because let me remind you that for tangent beta for order 1, actually I didn't show you that, but naturals demands also that the heavy Higgses are light. So we see this analysis here, and this is a plot that shows, has been shown many times by now, this is the Atlas CMS strong limits searching for inclusive tau decays, tangent beta MA plane. However, for low values of MA and tangent beta, all these channels open up, okay? And what I want to stress is that we should be looking at these channels very intensively, because we could be very much in this situation where these states are there, even if we are measuring the properties of the standard model Higgs very close, of the Higgs we have measured very close to the standard model ones. And this is shown in this plot where it's tangent beta versus MA. So these lines are the same as here, okay, the exclusion limits for Higgs to tau tau for two different scenarios, one where the Charshino channel is closed, and therefore you gain more in reach in Higgs to tau tau. But what I would like you to pay attention is to the dashed lines. The dashed lines are really cross-section times branching ratio of the Higgs into WW and CC, standard model normalized. So this is the case where there is no alignment, and so one would say that if I have measured that the deviation is less than 20% on the Higgs production to WW and CC, I would put a bound of the order of 500 GeV on the other Higgses. That is true, but not always. In the alignment limit, you have to look at these red lines, and so, for example, a 20% departure could imply that the Higgs could be as light as 300 GeV. So these searches are very crucial, and this is shown in the MSSM, but it's also true in SUSY extensions and in most general to Higgs doublet models. This is just to show that you can also look at indirect limits in the SUSY spectrum from rare decays. This is the direct searches, and this is actually what LHCb projections would do. This is standard model central value allowing for 30% effects on new physics from, in this case, minimal flow evaluation MSSM, but you can do it in many other cases. And so you see that you could explore indirectly higher regions in what was called the wedge of the MA plane. So, as we heard from Frank, if we want SUSY to, we have two options, correct? Either SUSY is close to natural, but is cleverly hiding from us. In that case, we have different options. We have these compressed spectra, and Frank showed the stop mass going, so the stop mass very close to the charm mass and LSP, so stop going to charm neutralino. I was very pleased to see the results of, I'm sure Iris, who is around here, Iris Freitas, is also happy, that the plots that were shown for initial state radiation were actually very close to what we proposed before the LHC started running, so that was cute. And then you can have things like stealth SUSY or R parity violation, where you have a lot of intermediate decays, a lot of checked activity, and so you run down in the missing energy. However, in all of these cases, I think that Atlas and CMS, as we saw from Frank's talk and from the prospects, are closing the gaps even from more in this direction. So now the idea is how we can do, as we said, we are closing the direction thinking that all particles are relevant for naturalness. So one direction theorists have gone is try to build natural SUSY models. And I will not go into detail because of time, but let me just tell you that the idea here is to connect the lightness of the third generation fermions to the heaviness of the third generation fermions. Okay? So basically address the flavor as part of the SUSY breaking mechanism. And what the other word says is to say, well, the top is so heavy, and therefore the stop can be lighter, however, is very different from the rest of the quarks. Okay? And the other thing that we want to do in this natural SUSY model building is alleviate the tension of the Higgs mass that needs sizable radiative corrections. Okay? The Higgs mass in supersymmetry at 3 level is just 91 GeV, so these radiative corrections have to be relevant. In the MSSM, this is the expression, depends mainly on logarithms of the stop mass over the top mass and on the mixing of the stop mass of the stop sector. So the MSSM requires either quite large stop mixing, which at the same time tells us that the gluon fusion cannot be very far away from standard model, or relative large stops that would probably make us a bit uncomfortable with naturalness. There are other possibilities beyond the MSSM, that is to add new degrees of freedom that contribute at 3 level, that contribute at these. And the main possibilities are to have new quartic couplings. This is what happens in models with extra singlets, or to have contributions to these quartic couplings that appear here through additional D terms, which is, say, that we do gauge extensions of the MSSM. And this usually comes with set primes at LHC, and we saw that they're being pursued a lot. I'm done? Serious? Okay. Okay. A couple of minutes to wrap up. Okay, I will not tell you anything about the model building. It's gorgeous. Well, this is good. If everything goes wrong, you need to look at PeV scale fermions, and since my colleagues did that, I will show you that you can actually have reached up to 100 TeV or so looking at EDMs and CP violation in K on decays. So in the last 0 minutes I have, okay, I will tell you that there are other kind of models that are models of composite Higgs. And so the idea is that we embed the standard model with the Higgs in a warp extra dimension, and the hierarchy is given by geometry. So everything that is Planck scale is in the UV brane, and everything that is TeV scale is in the infrared brane. The Higgs is here. In these models, the good thing is that warp extra dimension models address at the same time the hierarchy, the gauge hierarchy problem and the flavor problem, in the sense that the heavy quarks are localized close to the Higgs, and that's why they are heavy. The light quarks are far away from the Higgs, that's why they are light. And since all the KK companions, okay, all the extra fermions and gauge bosons that appear in these models, the KK modes, are also infrared localized, you naturally have what is called RS gene protection, because these guys and their KK modes do not mix too much, so flavor is naturally preserved. I won't say too much about that, but I will say that the other class of composite Higgs models are those that have the Higgs as a pseudo-Nambu-Goldstone boson. In RS models, this is also possible, but what I would like to say is that this is inspiring pions of QCD, and the idea here is that the pseudo-Nambu, since the Higgs is a pseudo-Nambu-Goldstone boson, is naturally light, because it appears as the pseudo-Nambu-Goldstone boson of the spontaneous breaking of a global symmetry by some underlying strong dynamics, and the Higgs mass at 3 level is protected because of this global symmetry, and it only appears at loop level when this global symmetry is explicitly broken. So there is a lot of model building in this analysis, in this type of models with pseudo-Nambu-Goldstone boson. Some of them tell you what is the UV completion. Some of them just assume that there is some UV completion and look at what would be the underlying strong dynamics that generates the Higgs as a pseudo-Nambu-Goldstone boson. So one thing I want to show here is that this is what you can do in these models. We are just an example. This is the signal strength of the Higgs going into gamma-gamma in QQH and associated production versus the signal strength in gluon fusion and TTH. This is ATLAS, all ATLAS limit, and these are all these models that we are looking with different embeddings of the fermions. And you see that even now, at least ATLAS, CMS would have covered all this actually, is trying to disentangle what is really the structure of the fermions in this type of models. So obviously with more sensitivity, we would be able really to pin down a bit what could be the structure of these pseudo-Nambu-Goldstone bosons. I won't say anything about this, but obviously all these models have, as a result, the fact that you have a lot of heavy fermions that are copies of the standard model fermions, and that's why the searches for different type of single top partners or doublet top partners or doublet fermions with eccentric charges are very interesting, and we heard from Frank that. Okay, so I won't say anything about the power of the dark side because they are too late, but I want to say that the last thing I would like to say is that in supersymmetry, we are cornering the WIMP miracle, and this is my last slide. So what we want to understand, this is the direct detection experiments, and this is the neutrino floor. And so if the Higgs, if the portal to dark matter would have been a set, the usual set boson, the cross-sections would be of this size and are already excluded. But if the Higgs is the portal, or the Higgses, actually, there could be cancellations of these cross-sections. And in fact, it is interesting that we push these direct detection experiments as low as possible because this contribution of this WIMP as a SUSY model to really either find the Higgs, the dark matter as a WIMP in supersymmetry or excluded will demand to really push things very much to this neutrino flavor. So I finish here, and I said that I think revolutionary advances in our understanding of the universe are really driven by powerful ideas and by powerful instruments, and I think the best example is the Higgs mechanism and the LHC. And so now we are entering a new decade with the LHC coming and with amazing possibilities for searching for dark matters in extraterrestrial experiments and deep underground. Thank you.
Thank you very much, Marcela. A very nice summary, although I know that you wanted more time. I understand that. A lot of material. Thank you very much. So unfortunately, because we are running really very late, the organizers asked me that, well, if you have questions, please contact Marcela during the coffee break. Thank you very much. And thanks again, Marcela,